Good morning, everybody. It is great to see how many of you have joined us here today, and welcome to this webinar hosted today by the University of Florence. The speakers today are Professor Dr. Andrea Brachelli, Rolling Stock Design, Manufacturing and Maintenance, and Dr. Gianluca Migna, Rolling Stock Advanced Design and Development from the University of Florence. Andrea is a professor at the University of Florence, lecturing on rolling stock design and homologation, on the railway tracking engineering. Founder and owner of a consulting company that worked for the most important car builders as well as for infrastructure managers. Skilled in structural mechanics, machine vibration control, management, correlation analysis, vehicle dynamics, troubleshooting, and forensic support. Designer and responsible for complex N&V and structural mechanics measuring campaigns, including data management and processing. Focus on rail industry, on rolling stock track and their interaction. Large experience on rolling stock homologation. He owns several patents on rolling stock running gears. Gianluca is a researcher at University of Florence with a master's degree in mechanical engineering and a PhD in industrial engineering. Research topics mainly deal with the railway vehicle's dynamics and structural behavior of railway safety critical components, while working also freelance for the consultancy activities about WeRail interaction management, homologation processes, and measuring campaigns. We encourage you to ask plenty of questions at any point during this webinar. Please type your questions into the Q&A box you will find at the bottom of the screen. At the end of the presentation, we present your questions and answer as many as possible. It is a pleasure to have Andrea and Gianluca with us today, and I would like to warmly welcome them now to take control and begin the session.
Thank you, ladies and gentlemen. Good morning, everybody. Welcome. Our presentation is structured in 5 parts, which of them 4 are the most important ones, and the last one is just the conclusions. I will take care of parts 1 and 3, and Gianluca of parts 2 and 4. So I start from an introduction about inboard bearings bogies and how to decouple the wheelset bogie maintenance, which is at the beginning of our study, research and development of a new geometry for tyred wheels. Basically, we know that since the beginning of the railway era, we got a mixture of inboard bearings bogies and outboard bearings bogies. Even the rocket was manufactured with 2 types of bearings. So the locomotives had inboard bearings bogies and the tender had outboard bearings. The same principle remained along the years for many decades and for more than 1 century or 1.5 centuries. And in all steam locomotives, like the Italian top locomotive or the German top locomotive or the French or even the British top locomotive, everybody knows the Class A4 by Sir Nigel Gresley, so it was one of the most famous locomotives in the world. They all had in common 1 component, that is the inboard bearings bogie. So this is certainly not new. It's something that existed since the beginning of the railways, but that in recent years has got a great revival or great fame because of some important features. Great Britain has been the country where the modern inboard bearings bogies were developed. Probably some of you know the studies of British rail research that led at the end of the 80s to the rollout of the B5000 bogie that was in 1989. I personally have the chance and the great pleasure of meeting one of the designers of a B5000 bogie. And a number of vehicles of classes were running in the UK in the last decades, equipped with inboard bearings bogies. The project was then developed by Bombardier, that is marketing today the clearly a developed bogie under the brand name Flex Eco. This Flex Eco bogie developed again along the years, and I know many colleagues in Derby that worked on this bogie, and recently it was widespread in the Aventra class of vehicles that has a number of classes, because it was this vehicle was bought by different operators. And if you look at the bottom of the screen, you see that as of nearly 3 years ago, more than 2,500 vehicles were ordered by 6 operators. So the inboard bearings bogies by Bombardier are widespread in the UK. Bombardier is not the only company developing this kind of bogies. Hitachi has developed an inboard bearings bogie for the trailer car for the IEP class. That's a huge program to renovate, to renew the fleet of intercity trains in the UK. The same concept was developed by Siemens for the SF7000 bogie that equips the Class 700, the Zero City Thameslink. This bogie was so successful that we'll go back on this in a few seconds. Then, more recently, CAF has delivered to Transpennine Railways some EMUs called the Class 397. You see some pictures of the vehicle. In the top right, you see the vehicle at Velim circuit in Czech Republic during testing, and in the lower picture somewhere in England, but I don't know where exactly. You see that this vehicle has brake discs mounted on the wheel web. Similarly, similar vehicles were developed by CAF as conventional trains, so no EMUs, but shuttle trains. This is a Transpennine Nova 3, and beyond the locomotive, that is a diesel locomotive manufactured by Stadler, CAF supplied the Mark 5A coaches. You see that the brake discs here are mounted on the axle, and the wheels have no components attached on them. The same vehicle, slightly different, is called the Mark 5 and is a Caledonian sleeper. You see some pictures. You can find plenty of pictures on the internet about these vehicles. What is interesting to see is that the last, to my knowledge, actor that developed an inboard bearings bogie is Stadler, that designed, I know personally the designer of this bogie in Valencia in Spain, the former Foslo company. And this is Class 777 for WeRail. And you see that there are some Jacobs bogies, so you can find conventional bogies as well as Jacobs bogies equipped with this architecture of inboard bearings. Outside the UK, outside the Great Britain, there are some interesting applications, very interesting applications. The ICE4 of the German railways, that's a train manufactured mostly by Siemens, but some rail cars, some car bodies, and the trailer bogies are manufactured by Bombardier. It's the same concept of the Flex Eco bogie. You see in these pictures the trailer bogies in the upper two photographs. In the lower photograph, you see two cars connected, and the rightmost one has a motor bogie by Siemens, and the leftmost one has an inboard bearings bogie. You can see the difference in the architecture, the wheel diameter, the wheelbase, and all of the differences of the two bogies that are immediately apparent when you look at this picture. The idea, the concept of inboard bearings bogies is so successful that Siemens decided to develop a specific platform for regional railways. This is an EMU, and the concept of SF7000 was developed to SF7500. which, as written in this leaflet, has a greater energy efficiency, a higher flexibility, and so a higher and predictable profitability. The reason for the large use of inboard bearings bogies in the UK dates back to October 17th, 2000, when the Hatfield accident put up an evident what's the problem of rolling contact fatigue and on track friendliness. Since then, a number of studies were developed in the UK, and today, to my knowledge, Great Britain is, or Network Rail, is the infrastructure owner that has the most advanced track access charging method that rewards who damages at the minimum the rails. And inboard bearings bogies have a distinct advantage from this point of view. So if you want a train that has a low, that introduce a low track damage, you have probably to use just an inboard bearings bogie. This architecture is the best starting point for our study, because if you look at the pictures that, if you scroll back once you have access to this presentation, you see that many of these wheels are really in sight. There is almost nothing in front of the wheels, and so the wheels can be accessed from outside with without the limitations of an outboard bearings bogies that have the axle box arm and the primary suspension. If you look at the tyred wheel, this is a concept that Gianluca will develop more in detail later. The shape, the wheel consists of three parts: a wheel center, a wheel tire, and a retaining ring that in the UK is also known as Gibson ring. Today, wheels are designed for infinite life and axles are designed for infinite life. But as a matter of fact, monoblock wheels are scrapped when the thread or the flange are worn, and the whole rest, the whole wheel is scrapped, and despite the fact that it was designed, I repeat, for infinite life. Axles as well have a finite life, because removing worn wheel sets and installing new wheels may damage the wheel seats on the axle, so the axle has to be reprofiled from time to time, and at the end it results in the need of scrapping the wheel set, sorry, the axle, even if it was designed to have an infinite life. So also axles at the end have finite life. The problem of tyred wheels is maintenance, because maintenance of tyred wheel is particularly expensive. I have shot some pictures in a workshop that is homologated. It is qualified to perform maintenance to tyred wheels. These pictures were not shot 50 years ago, but just a couple of years ago. And you see, it looks like we are in the 50s or last centuries, but it's just 2018, and this workshop is in Italy. But you see that everything is not automated. Everything is manual. So it's just the operator that has to decide the diameters, check everything, and clearly this is a nightmare from a costs and from working time point of view. So going back to our inboard bearings bogies, we had two ideas. The first is changing only the tire. The second is changing the entire wheel. Clearly, these 4 bolts that you see here are not intended to remove the wheel, but are just intended to keep in place the cap that protects the bore of the axle that is used for ultrasonic testing of the axle. But the idea would be to have the possibility of changing the wheels as this little child does. And this is what will Gianluca explain in part 4. So it's part of our other ideas. We will not discuss too much about this today. And so I would like to pass the microphone to Gianluca now.
Thank you, Professor Berciali. Good morning to everyone. Okay, I'm starting the second part of the presentation. In this second part, we pass from bogies to wheels, and we are going to see the design, the manufacturing, and testing phases of an innovative tyred wheels that we have developed. As explained briefly by Professor Bocciali, today monoblock wheels are the preferred solution for from the vehicle manufacturers, and they have almost completely replaced tyred wheels. There are several reasons about this choice, but the main reason is maintenance. Monoblock wheels have simpler maintenance because tyred wheels are made of three components: the wheel center fitted on the axle, the tire fitted on the wheel center, and finally a retaining ring is applied manually to complete the assembly. The procedures and operations to complete this assembly are quite long, and often several machines and tools are needed, while in monoblock wheels, the replacement of the wheels is the only operation, and there is no need for special tools or something like that. So a big automation has been reached in the last years. So the main advantage of having a removable tire, and therefore reducing the purchasing cost, for example, or having an infinite life component as the wheel center, just like the axle, these advantages are cancelled by the tire fitting and removal processes. Here you can see a short simulation of the tire fitting, and the mounting parameters such as the tire, the thickness of the tire, of the mechanical interference between the tire and wheel center bring also to high stresses and strains in the wheel center. So tire fitting has to be carefully defined before in the design phase. Here you can see some pictures of a tire replacement of a tire wheel. In the top left picture, you can see the wheel set placed on a wheel lathe and the mechanical removal of the retaining ring. So the wheel set is moved to an alternating saw where the tire is cut, and then it is extracted. Often the extraction of the tire leaves some scratches on the wheel center, on the external part of the wheel center, and therefore it has to be machined again, and therefore the diameter changes, the mating diameter changes, and the new tire have to be adapted to this new diameter. So there is no interchangeability between components, and the process is an adaptive process. And one way to remove this problem is to use heating to heat the tire and remove it. Here you can see an induction heater applied to a worn tire, but the mechanical removal of the retaining ring has to be maintained. Here you can see in the yellow box the grooves leaves by the wheel lathe to mechanically remove the retaining ring. So the retaining ring is the main obstacle for the improvements of the maintenance of tire wheels. And the question is if it is really needed, and the answer is no. The reason of using a retainer ring has to be found considering the tread braking problem. Tread braking in all railway vehicles is critical, especially if considered for freight vehicles. Also, monoblock wheels suffer from tread braking, and cracks could be generated. And a specific design need to be applied also for monoblock wheels. Tyred wheels were developed when thread braking was the only solution, and therefore all the mounting parameters such as tire thickness, mechanical interference between the tire and the wheel center were developed to withstand this kind of thermal input. But in 1968, some tests have shown that the losing time of tire could be lower than 10 minutes if a continuous braking power is applied. So tyred wheels are unsuitable for drag braking and thread braking. The retaining ring is the only component that locks the tire radially when the problem of easing during thread braking is generated. But today we have disc brake in almost all passenger vehicles, and we have electric brake from the motors, and we have other solution, and thread braking is not so critical anymore, at least for passenger vehicle and not for freight vehicles. So we can do something more to improve this kind of wheel design for vehicles not equipped with thread braking. And the solution that we have proposed is a simpler dovetail coupling, so a double conical coupling that can be easily machined with modern CNC machines. Obviously, the dovetail in this picture is amplified, but we can see some real picture in the following. And thanks to the elimination of the retaining ring, we can do an easier fitting and removal of the tire. And using heating, for example, an induction heater, to heat the tire and remove and fitting them. Some finite element calculation have been performed to understand if the coupling is safe from a mechanical resistance point of view. So we have simulated a brake pressure test on the tire, and we have seen that no displacement between the tire and wheel center is reached even with a force and lateral force 10 times greater than the maximum lateral WeRail contact lateral force. As you can see in the picture below, we have developed an asymmetric coupling because the lateral forces at the WeRail contact are different according to the direction of application of the lateral force. This comes from the design code from all railway wheels according to EN standards. So the coupling is safe, and therefore we decided to produce some prototypes. Here you can see some pictures about the machining of the tires, the machining of the wheel center, and the results of the on both of them are visible here. Also some other kind of measurements were taken to verify the dimensions obtained by this kind of solution and to verify the correct shape of the machine surfaces. Then we mounted the tires on the wheel centers. Due to the shape of the new coupling, the mounting has to be done vertically, so it could be a problem, and but we have done the solution later. After the cooling of the tire, we have performed some measurement, obviously, to verify that all the tolerances according to EN standards were respected. For example, axial runout, radial runout, width gauge, and unbalances were measured, and even if fully finished tires were used, all these kind of measurements were good in good tolerances. So no further machining or operation was needed after the mounting of the tires. We prepared 4 wheel sets to be assembled on 2 bogies, so 1 coach. And we performed 2 days of testing. Here you can see a picture. During this test, several stopping and starting maneuvers were applied to verify the strength of the coupling. The vehicle that we use was tread brake. So we monitor the temperature using a thermal camera, and even if some emergency braking maneuvers were performed, no displacement or no problem were found during this kind of solution. So the final solution has been found considering a different kind of coupling, but it is only dictated by advantages in mounting procedures. So here you can see the final drawing. We not use anymore the dovetail, but we have a single conical surface, single tapered surface, and we restore an abutment on the left, but it is used for an axial reference during mounting, and in this way the mounting can be done also horizontally and not vertically as shown before. So this kind of solution will be more clear in the next presentation, and I give the microphone to Professor Barciali.
Okay. So we go again with a third presentation that's about the tire changing station. Okay, probably you don't see me, but that should not be a problem, I think. Basically, there are some keys to the just-in-time success of this technology that are the 5 steps that you see there. So there is an early detection of what can be wrong in the wheel tire, in the wheel tread, on the wheel flange. And there should be an automated selection of the maintenance operations. And there would be the need of some people, some personnel capable to perform minor manual operations. We'll see what they are. And the availability of an automated system to replace tires. And of course, this will ensure continuous flow of data for traceability and for management of the new material, purchasing material, and scrapping old material. So let's look at the steps of a fully automated robotized station we have conceived. First of all, the train goes back at the depot, let's say around midnight, at the end of the service, and the measuring station checks if the wheels have something wrong in terms of wear, for example, thickness, height, or slope of the flange, or if there are any RCF damages that introduce high vibrations in the rails, like spalling, shelling, or any other type of RCF that gives any irregularity on the wheel tread surface. If there are wheel flats that are not compatible with service, or more generally, if there are any plastic flow or wear, like tread hollowness or rollover, that have to be corrected. Normally, all these problems can be corrected by underfloor lathe reprofiling, but sooner or later the wheels will reach the end of their lives, and the day will come when the wheels have to be changed. If the wheels are tired, and with this plant, everything can be done automatically. Let's suppose that the train goes on the measuring station, and the measuring station raises an alert to the control tower. The train is diverted to a specific track on steel columns where workers prepare the axle to be changed, or sorry, better, the wheels to be changed, removing the parts that may obstruct the accessibility to the wheels, like stirrers, earthing contacts, brake calipers, anti-yaw dampers, or whatever may obstruct the accessibility to the wheel. In the meanwhile, a fully automated warehouse is used to pick up a couple of new, fully machined tires, so they are ready to be installed. The tires are laid on automated guided vehicles, automated guide vehicles that reach the workshop and enter the area that is normally protected by safety barriers for several reasons. We'll see them later. And the tires are brought near the robots that will perform the maintenance. The tires are then, the new tires are then picked up, grasped by a special end effector, and put on the heating stations that are on the right side in this picture, where induction heaters can raise the temperature up to 300 Celsius, which is compatible with all existing tires according to all the regulations on tires. So this temperature is certainly allowed. The heating is not immediately started because the tire removal is longer than heating, so heating will be started later. The train is then moved close enough. There is tolerance of ±1 meter in our design, and in a special cart is moved along the track in the pit under the vehicle until it reaches the defective wheel set. You see that there are some 2 jacks that lift the wheel set up by properly interfacing with the axle box. So the cart places itself exactly under the axle boxes, lifting up the axle. Then a rubber roller starts driving the axle. This we have checked, it can be done with motor axles as well as trailer axles, so it can work without damaging the paint. In the meanwhile, high power lasers heat up the worn tires. This is a quite lengthy process. It may take 10 to 20 minutes, depending on the amount of material that has to be heated. Because if you have a fully worn tire, its thickness and the amount of material to be heated is certainly lower than a new tire that has to be replaced for other reasons that I cannot imagine. But in that case, heating times can be extremely longer, much longer. Then, when the tire is loose on the wheel center, the robots pick up the worn defective tires while rotating, and they lay the worn tires on the AGVs as before. At the time, the new tires are already hot at the right temperature at 300 Celsius, and the robots quickly move them to the right location and install them on the wheel centers. What's interesting is that the end effector, the clamp, the hand that moves the tires can rotate. So cooling is obtained while rotating, and this means that cooling is uniform, and the robots remain in this position until the cooling phase ends. Then, very quickly, the wheelset is lowered down on the track. When the temperature is at around 70 to 80 Celsius, it may take some 15 to 20 minutes to cool down sufficiently the tire. The train is pulled back, all the mechanical parts are refitted on the bogie, the train leaves the shed, and all the tires, removed tires, are brought to a fully automated scrapyard ready to be recycled. What's interesting is that the whole process may take less than 5 hours. In this video, you can see the whole process. What I've shown you until now are in fact just screenshots taken from this video. I would like to thank ABB Robotics for their support on this project. We have used ABB robots, industrial robots, so certainly which is absolutely affordable from our point of view. And I also would like to thank IPG Photonics, that is a worldwide leader on lasers. And so they provided all the information to integrate high power lasers in this process. So we have the greatest confidence on the fact that heating by laser can be done, because this has been assessed and checked by the people from IPG Photonics, that are the world leaders on this technology. Last but not least, I would like to say that all the environment that you see here has been modeled by using SolidWorks CAD system, and that the movements of the robots that you have seen are not just an animation, but are the results of a robots programming by using Robot Studio software. So if you have a robot like this, you can simply upload the software that we have developed, and the robots performs exactly what you have seen in this video, including all the validations in terms of masses, of inertia calculations, and so everything is. This is not just a nice video; it's the result of a real simulation. This is the end of the video. It lasts some more, nearly 1 minute or something like that, but you have seen, I think, the most important parts. So while we see the old tire removing and the new tire going in place, I can anticipate that at the end you will get a link to see this video on YouTube, and you'll get also the website to download all the papers about the new tired wheels concept. Okay, I think we can stop now. You can see that at your convenience at home. So I go back the microphone to Gianluca again.
Okay, thank you again. The fourth part of the presentation is quite brief. It should be a few minutes just to introduce some other development that we have formed in terms of improvement of maintenance of railway vehicles. The first is the Liberty Wheel, that it is a product, it is not only a study, and we have applied the principle of the conical mating to a brand new wheel center. The wheel center that you can see here in the picture is made of house-tempered ductile iron, so it is a light and optimized wheel center. Radial and axial stiffness are carefully defined by finite element method. We have got also lower mass and lower noise emission. Here you can see some pictures, but I think there is no time to go through this topic. Some pictures also from the testing point of view of this kind of product. Here you can see some fatigue tests that we have performed, and also some inline tests that we have made with this kind of solution. Another kind of solution is called air wheelset. Air stands for apparently independently rotating wheelset, and it is specifically designed for inboard bearings bogies or inside frame bogies. And the main advantage is that all the main components, for example, the wheels, the brake disc, and the bearings, are grouped in only one element, and so we can perform the removal of this kind of component and maintain completely alone these kind of components. The two wheels that are then connected by a torsion shaft and equipped with a torque limiter to let the wheels freely rotate in sharp curves. The last one is 4L bogie that we have developed as a replacement for freight bogie, the most common freight bogie in Europe, Y25 bogie. And the solution is quite innovative with a primary suspension placed horizontally and connecting the front and rear axle. So we have clear advantage in number of components. We have lower mass, lower moment on inertia, and therefore we have got improvements in terms of truck friendliness and so on. Both the 4L bogie and the air wheelset are patented solution, so they have got the approval of the patent office for Europe. So I can conclude here, and I give the microphone back to Professor Bacciari.
Thanks, Gianluca. So I share my screen now. Okay, so the conclusions and some hints for further developments if you like them. So first of all, we have introduced a new technique to modify tyred wheels. This has been done after some calculations with non-linear finite element models, and that gave us sufficient confidence to start the project. It is based on fully CNC machine tires, something which is widespread and commonly used today, so that's not anything new. And that highlighted the fact that the Gibson ring or retaining ring is not necessary, so we removed it. It dramatically simplifies maintenance operation of tyred wheels, because you just purchase fully machined tires and you install them directly on wheel centers without any mechanical operation. So this gives a possibility of having an infinite life of wheel centers as well as for axles without introducing any damage. So this is something that our grandfathers did. So the idea was not of changing wheel centers and axles, but just changing the tires. The technique was line tested in demanding conditions, so with block braking in sharp curves and in harsh conditions, and the behavior was fully satisfactory. And we got the interest from many railway operators because this can really cut the costs of maintenance. And I can only tell you now that we have a worldwide cooperation in progress to retrofit this type of tires on an existing fleet. Please note that this technique can be applied to all existing tyred wheels. And it's a very straightforward application, but that it can also be used on existing monoblock wheels. So if you are facing too high costs or you want to be autonomous in changing the tires, you can change the wheel center and go back to the very good and old tired wheels. Then we gave you some ideas of a fully automated system to replace the tires. And this gives the possibility of changing the tires only on condition, wherever a track on steel columns is available. And the cycle is fully automated except for some preliminary operations that you have seen before to remove components that obstruct the access to the wheels. And the robotized changing station is totally unmanned, integrated in the digital system of your depot, of your workshop, including spare parts management. And both wheels tire replacement, of course, of a wheelset requires less than 5 hours. That means that you can go back at night with some defective wheels and you can go back to service directly the morning after without any need to replace the vehicle or to stop the vehicle or change the bogie or anything else. You just have to change the tire, and you can do that with this automated system. We have also briefly introduced some other concepts, the air wheelset, the Liberty wheels, and the 4L bogies. We have produced a massive number of papers in conferences and published in journals. For example, last year at the International Wheelset Congress that was in Venice, in Italy. And we are open to your suggestions for cooperation. We are at your disposal to give you more details and all the stuff you may need to implement to use these techniques in your company or in your railway. Thank you so much.
Andrea, Gianluca, thank you very much for a fascinating presentation. That was excellent. I've got some questions to ask you, so I'm going to dive straight in. First question for you both. Is it common practice now to decouple wheel set maintenance from bogie maintenance, or is this more future looking?
It is, I answer. It is more future looking for the robot station, for the robotized station. It is already, it's getting real for the tapered tires. So we are on the way, on the process of using the first tied wheels with a tapered mating surface without retaining ring in the next month.
Thank you. Question from Punit. What are inside bearings and what are its advantages?
Inside bearings, maybe we can discuss this in a different place, because it's a general architecture of a train. So axles have to have bearings. Normally they are placed outside on bearing seats, but as I explained, inboard bearings have distinct advantages in terms of running dynamics, on track friendliness, on masses and more moments of inertia. So there is a huge literature on inboard bearings for this.
Thank you. Another question from Punit. If tired wheels are expensive to maintain, then why use it?
Thanks for the question. That's exactly what we tried to avoid. So everybody knows that tired wheel sets are very costly to maintain. With our system, their cost becomes nearly negligible.
Thank you. Question from Gianluca. Please expand more on the different machines are needed for tire removal process.
Okay. In the worst case, we need a wheel lathe to mechanically machine the retaining ring. We need an alternating saw, so to cut the tire, an extractor to extract the cut tire to respect to the wheel center, and then we have to move again the wheelset without tires to the wheel lathe to perform the machining of the external surface of the wheel center, because some scratching could appear while removing the cut tire. And then we have vertical lathe to machine the tires, and so on. So there are,
if I
yes.
can add something, we have given a couple of years ago a specific paper on tired wheel maintenance and equipment needed to maintain tired wheels at a conference in Spain. So whoever is interested, please browse the internet on our website, www.andreabracciali.it. Maybe I can share again the screen and show you the last slide. Maybe you can see it now on your video, on your screen. You see a website here, and if you check at that page, you can download many papers about inboard bearings, bogies, about machining, workshop practice, maintenance, and so on.
Thank you very much. Next question from Nicholas. Is it possible to use this type of wheel in freight cars? And what is the maximum axle load allowed?
No, it is not possible to use this type of wheels in freight cars if braking is applied on threads. So if you use disc brakes, it's possible, of course. If you use thread braking, I don't think it's a real alternative. About axle load, there are no limitations. Whatever.
Okay, thank you, Andrea. Another question from Philip. Could this process to remove the tires be used as part of an extension of the wheel lathe?
Why not? We have to discuss about that. So we have some practice of machining and some practice of how workshops are managed. So whoever is interested, we can. You have seen some pictures. Gianluca has shown many pictures taken in the workshop. So we have an idea of how a workshop works. So everything can be done. So if you want to work with us, we are glad to help and to develop something together.
Thank you. Next question. Nice photos. Were these examples done on site at the university workshops, or were they done at a partner's workshops? How recent are they?
Now, unfortunately, our university is not so well equipped with machine tools. So they were all taken at an external workshop, which is a quite famous workshop in Italy, and they perform very accurate machining, but probably any workshop performs accurate machining. And we have decided all the tiniest detail with these people, and we are particularly happy about the results. Everything was performed between 2018 and 2019, so in the last 2 years, and we have plenty of stuff in terms of pictures, designs, drawings, and specifications for workshop.
In regards to the video showed, and you were kind enough to let us know about the partners, ABB and IPG Robotics. Did you go to them, or did they come to you to form this partnership on the project?
We went to them.
Yeah.
We decided to involve them because we needed. I'm sorry. This presentation is not very academic. I understand, because we relied a lot on industrial resources. And so we had all industrial partners, and we only wanted the best, to make sure that the project was feasible and was not an academic idea. But this is something that led to real products running on real rails. So this is not a dream, this is true.
Thank you very much. Next question for you. Apologies for my ignorance. I have a commercial job role. Can you explain in layman's terms how this can reduce time and errors in the maintenance process?
Well, it's very simple, because maintenance process today is very complicated, because it needs machine tools and measuring equipment. So there has to be a metrology area area to check the equipment. With the new system, all this disappears because you just purchase fully machined tires, or you install them, you hit them, you install it on the wheel centers, and that's all. There's nothing to check, there's nothing to machine, no machine tools, no metrology, no possibility of mistakes by operators. It's as simple as changing the wheels of your car.
Thank you, Andrea. Next question for you. How widely spread is automotive wheel maintenance via robotics?
I think it's not spread at all. It doesn't exist, simply. Everything is performed manually with incredible costs. Consider that a robot like this, without the end effectors, so the bare cost of the robot is less than 50,000 euros. So we can say that it costs nearly nothing. 20 years ago, a robot like this costed 1 million euros. Now they have a very low street price, let's say. So all this is affordable. We didn't do something that's like putting a satellite in orbit around the Earth. This is something that can be done with limited resources. It is a scalable architecture. You can decide if you want to do everything automated or leave some parts, some phases manually. You can, for example, move the tires from the warehouse to the mounting station manually. It's up to you. So we have given an idea, a picture of what could be done at the best. If you have scarce resources, you can save money and doing some parts as you always done them.
How long in the future or close to now do you think this will take place?
Let me say, in our country, never, because we don't have any inboard bearings bogie. So the automated, the robotized station is designed for inboard bearings bogies, where you don't have the axle box in front and there is no primary suspension in front. So you have to have that kind of architecture to be able to introduce the robotized station. In the UK, that it's much more probable.
So is it purely based on the infrastructure that that country might have to go forward with this?
Well, if you mean type of rolling stock, yes. Infrastructure for us is something more related to civil engineering or to permanent way, okay. But I think that a country like Great Britain would be perfect to introduce this technology, because all the trains, all the manufacturers in the world, whenever they cross the channel and come to Great Britain, they have to design and implement, build and put into service inboard bearings bogies. So whoever you talk to, he will be interested in this kind of technique.
Thank you very much, Andrea. I think you've answered this question, but I'll quickly ask it. Did you develop this technology at the university? If yes, when was it created and developed?
We developed at the university and partly with my consulting company. You mentioned in my CV that my biographical notes that I founded a consulting company some more than 25 years ago. So I put some resources personally to develop this project, as well as the university, as well as all the industrial partners that worked on this project for free.
What's your consulting company called, Andrea?
It's called AB Consulting, with not much fantasy, I understand. Okay.
Well, nice bit of promotion for you. Next question for you. Which has provided more effective, changing the tire or changing the wheel?
We did not prove the changing the wheel technology because wheel set manufacturers did not like our idea of changing the wheel with brake discs and the bearings in it, because this dramatically reduces their market. So we proposed the air wheelset to nearly all European wheelset manufacturers, but they decided not to proceed with the concept. One of them also proposed to purchase the patent, but we did not reach an agreement on that. So we did not sell the patent.
Okay, it's the same question, but it's which has proved more time effective, changing the tire or changing the wheel?
Changing the tire requires less than 5 hours, as I said before.
Yeah.
Changing the wheel, I have no real numbers because we have no idea, but it's a matter of removing a crown of bolts with an extractor. So it could take even less. So maybe in 2 hours, you can remove a wheel and you have a new wheel with new or worn brake discs, with new or worn bearings, as you prefer. So you can split completely the maintenance of a bogie and the maintenance of a wheelset. That's one of the main reasons for developing that, to completely split the maintenance of a bogies and of a wheelsets.
Thank you very much. Guys, I just want to finish with what a couple of people have just written. Hugh's written, great webinar by Andrea and Gianluca. Thank you.
Thank
And
you.
Merlin Hintz has written, very interesting presentation. Thank you very much from Colombia.
Oh, okay. Someone said, if I can conclude, someone said that this technology is better suited for poor countries. I don't want to argue what means poor country. It's something that it's out of my scope. But certainly this is a way of saving a lot of money, a huge amount of money. So if you're not particularly rich, or if you want to start saving a lot of money, that's a good way to start.
Thank you very much. Ladies and gentlemen, I would just like to say a big thank you to Andrea and Gianluca today for an excellent webinar and a really good Q&A session. The webinar today will be on demand for you to all rewatch. Once again, I would like to say a big thank you to Andrea and Gianluca from the University of Florence, again, for an excellent presentation. Thank you to everyone for attending, and we look forward to seeing you all at our next WeRail webinar. Thank you all and goodbye.
Goodbye.